There will come times where we want to consider a much more complicated barrier than simply a step barrier. Something that goes from A to B. And it might look like this. In which case, what we do here is approximate this much more complex barrier with a series of stepwise potential barriers, each with a beginning coordinate xi and ending coordinate xj. In this case, e to the minus alpha xi minus xj, that's approximately equal to 1 because xi and xj are so close to each other. So the probability of transition for a thin barrier will approximately equal e to the minus 2 alpha xi minus xj, because in our previous expression, the ratio out front will approximately reduce to 1. Well, that works only for a thin barrier, and we're planning on going through a lot of barriers. So it's the probability of transmitting through n of these very thin barriers. That will equal the product of probabilities. And if each one of them looks something like e to the minus 2 alpha x2 minus x1, e to the minus 2 alpha x3 minus x2, on up to e to the minus 2 alpha xn minus xn minus 1. And this will equal e to the minus 2 sum over j delta xj alpha. Which, as this sum goes to an interval, becomes e to the minus 2 interval alpha dx, going from A to B. We'll plug in what alpha is. This becomes e to the minus 2 interval from A to B, square root of 2m u of x minus e dx over h bar. That's the expression for the probability. And it works whenever I can build up the potential as a series of stepwise potentials, as long as the potential isn't varying too rapidly with respect to x.